This video is going to cover pre-calc, section 12.1, day number 2. And the majority of this is going to be about whether a limit exists or not. When do limits fail to exist? But before we get into that, we're going to do another one here, using a graph to find a limit. If a limit exists and you have a graph, it's usually a good idea to look for the hole in the graph, and usually the limit is the height of the hole in the graph. So here we got a piecewise function, kind of a weird one. This top piece of the piecewise says if x is not equal to 3, your output value is 2. So for any value not 3, the output is 2. If I'm here at -1, the output is 2. If I'm at 0, the output is 2. If I'm at 1, if I'm at 2. I think you get the idea that no matter what, if I'm on the x-axis at any value that's not 3, my output is 2. And then if x is equal to 3, the output is 0. So here, our function is defined at this dot on the x-axis. And that's why we have this hole in the graph above. And this is also a good point or example for me to point out some notational differences. If I write f of 3, that would be equal to 0. So here, when I go to 3, the function is defined at 0. That's when I hit that dot. But the limit as x approaches 3 of this function f of x, well, that limit is going to be 2. Okay, let's go back to the graph. If I'm here at 2.5, my output value is up here at 2. I could get to 2.9 and I'm still at a height of 2. I could be at 2.999, 2.999999. I could get infinitely close to 3, and I'm always up here at this height of 2. So the limit as we approach 3 is equal to 2. F of 3 is 0, but as we approach, it's equal to 2. So a function can be defined at a very different number than as we approach. And again, if you're going about it graphically, look for the hole in the graph. Usually the limit is the height of the hole in the graph. Here's our hole. The height of that hole on our y-axis is 2. Now, limits that fail to exist. Next, you're going to study some limits fail to exist. We've got 3 of them. Here, example 6, it says comparing the left and the right behavior. So it says then, show that this limit does not exist. The limit is x approaches 0. And we have a numerator, the absolute value of x divided by x. Remember, the absolute value bars are going to turn that number, whatever's in there, into a positive. And if I remember right, I did not put this in your notes, so let's come up with a little graph here. Okay, now it says we're approaching 0, so that means we're approaching the origin. And let's just pick some numbers here. I'm going to go over to the right-hand side, the positive side here. And let's just take a look at maybe 2 and 1. If I put 2 in there, I get the absolute of 2 over 2, which is just 2 over 2, and anything divided by itself is 1. So I would be up here at a height of 1. If I put 1 in there, positive 1, I'd get the absolute of 1 over 1, which is 1 over 1, or just 1. And that's going to be true for any positive value of x. 1.5, any number between 1 and 2, I'm also here at a height of 1. But as I get closer, now, I could put in decimals. 0.0001 in bars divided by 0.0001. That's always going to be equal to 1. But as I actually hit 0, I get 0 divided by 0, which would be undefined. So that means our graph has a hole in it there. Let's see what happens as we come in from the other side. -1 and -2. Let's put the -2 in there. -2 in the numerator in bars divided by -2. So again, the bars are going to make that a +2, but now our denominator is negative. It's still 2 divided by 2, which is 1, but now it's going to be a -1. Same thing for -1. Absolute value bars make the numerator positive. The denominator remains negative. So again, it divides out to -1. So as we're approaching in from this side, we're also undefined. So there's what the graph looks like. It's pretty crude. Here's the book's graph. So as we're coming in from this side, we're down here at -1, hole in the graph. And then up here, we've got another hole in the graph, but then we pick back up, and now we're up here at +1. So this, and this, I'm going to show you this a little early. It's not actually in the book just yet, but a little notational thing that's coming pretty soon here. I'll do blue for this one down here. This is the limit as x approaches 0, and I'm going to put a little sort of like an exponent up here, a superscript of a negative sign from the minus side or from the left side. So I'm approaching 0 from the left side, and I'm just going to write f of x for my function. That limit, we're down here. Again, a limit is a number on the y-axis. That's -1. But I'm going to come up here in red. The limit as x approaches 0 from the right side, from the plus side, from the numbers to the right of 0, that limit is equal to +1. So here again, we got this special notation. We're approaching here from the left side, we're approaching here from the right side. They each have their own limits. So now I can sort of combine these, the limit from the left and the right, and make it one limit, the limit as x approaches 0. Now I don't put a plus or a minus there, so it's implied we're approaching from both sides. This limit does not exist. It failed to exist, and the reason is we have different behavior from the left and the right. Or you could say we're approaching two different limits. One limit from the left side, one limit from the right side. So again, to abbreviate DNE, and the reason is we're approaching two different numbers. This limit, this function, is approaching two different numbers. Two different numbers from the left and right. From left, right. Usually in the homework or on any AP test, if you're going to state that a limit does not exist, it's always a good idea to say why. And here's our first reason why. Because we're approaching two different numbers. If I compare that to here, as we approached from the left side, our height was 2. As we approached from the right side, our height was also 2. So since we're approaching the same hole from both sides, we can just make that one limit and say that limit is equal to 2. So first reason of 3, why a limit does not exist, different left and right hand behavior. We're approaching two different numbers. So here's a couple for you to try. Find the limit here. This is just like the first example. This one's like the second. So of course, pause the video, try the problems out, and see what you get. All right, let's see. This one, if we wanted to sketch a little graph, which why not? If our x value is equal to 2, we're at 0. But anywhere else that's not 2, we're going to be down at -3. So down here's -3, and our graph would look something like this. So it says find the limit as we make the approach. So here is 2 on the x-axis. As we are approaching from the left, it's like we're tiptoeing along this piece of the function, the line here. We're getting real close to that hole. So as we're approaching here from the left side, that limit is -3. And if we hop to the other side and we sneak up on it, we tiptoe up to this side as we approach from the other side, that limit is also -3. So we can write the limit of f of x as x approaches 2, well, that's equal to -3. Usually the limit of a function, it's going to be the height of this hole on the y-axis. Okay, this one here. Show that the limit does not exist. We could, I guess, make a graph out of it and maybe come up with some notation that will explain it. Here we're approaching 1 on the x-axis. And I'm just going to put a number beyond 1 over here. We'll just go do 2, and maybe we'll do -1 to see what's going on. Well, let's do the 2 first. If I just put a 2 in there, I'm going to get in the bars 2 minus 1, and that'll be a 2, or 2 minus 1 is 1, times this 2 is 2, over down here, the same x is 2, 2 minus 1 is 1, so that's equal to 2. Now if I put the -1 in there, again, let me jump back over here. So at 2, we would be up here at 2. And that's going to be true for any other positive number greater than 1 as we approach. There'll be a hole from that side. Now if I put -1 in there, I'm going to have 2 times -1 minus 1 is -2. And that's going to be divided by -1 minus 1 more is -2. So the numerator I multiply and get negative, or the bars. The bars make this into a +2, and then we multiply to get a 4. This denominator is -2, so we divide that and get -2. So we're down here at -2 as we approach in from this side. We got another hole in the graph. Oh, yeah. Yeah, this is -2. I guess I shouldn't have that down so far. There we go. And then we could write, with all our notation, the limit as x approaches 1 from the left side. Now I'm not going to rewrite all this. I'm just going to write f of x. That limit as we approach from the left is -2. And then we could also write the limit as x approaches 1 from the right side, from the plus side, from the numbers bigger than 1 of the same function f of x. Well, that's +2. And then overall, since here are 2 different numbers, we're approaching from the left and the right, we can write the limit as x approaches 1 of f of x does not exist. It fails to exist because of the function behavior. From the left, we're approaching one limit. From the right, we're approaching another limit. We should be approaching the same number for that limit to exist. All right, 2 more reasons coming up why a limit will not exist. Here's one called unbounded behavior. I've said before, a limit is a number on the y-axis, a number that we can pin down. So let's see what's happening here. I guess let's do a little table. Why not? We're approaching 0, and we're going to approach it from both sides. We can't plug 0 in directly. 1 divided by 0 squared, 1 divided by 0. That does not exist, so something's going on there. There might be a limit. We'll try to figure it out. As we come in from the left, we could do numbers like, I should have gave myself a little more room here. -1. Oops, where'd my pen go? -1, -0.1, -0.001, and -0.001. Dang it, where'd that go? Oop, come on. 0.001. On the plus side, we'll just do the reflections of those. +0.001. .001, 0.01. Oh, I guess we skipped .01. No biggie. 0.1 and positive 1. We'll do the positive numbers first. If I put a 1 down there, 1 squared is 1. 1 divided by 1 is 1. So if we was graphing this, we're approaching the y-axis at positive 1. This is not to scale. We're here at 1. Let's get closer. 0.1. If we square that, 0.1 times 0.1 is 0.01, and we divide that into 1, we get 100. So if I move over 9/10 of the way, I'm already up way up there to 100. Let's jump over another decimal. 0.001. You square that. So if you square it, it would be 0.00001. You divide that into this one. 0.0, that will be 1 million. A mil. So we've gone up the y-axis to a million. Sneak one more zero in there, 0.0001, square that, it gets even smaller. Divide it into 1, you're at 100 million. So as we're coming in here from the plus side, it's like the closer we get to the or the y-axis, the steeper and steeper we're going to climb. Are we ever going to touch it? No, because that would be like dividing by 0. If we jump over here to where the negative numbers are, notice in the denominator we're squaring that x value. The negative will square away, and we'll divide it into the 1, and our answers are going to be reflections of what we found on the positive side. So here will be a 1, a 100, 1 million, 100 million. So as we come in here, I'll switch to red ink. From the plus side, we're also headed up, 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 up to infinity. So let me get out the book picture a little better than mine. There we go. Kind of looks like a volcano. I could draw some red up here, put a little lava coming out of there. But we cannot touch the y-axis. That would be dividing by 0. As we approach, if we're not allowed to touch the y-axis, as we approach it, there's only 2 ways to go. We're going to be forced to go up to infinity, or another function might force us down to negative infinity. Same from the other side. As we approach, this vertical asymptote, there's only 2 options: up to infinity or down to negative infinity. Either way, that's called unbounded behavior. So here we could write the limit as x approaches 0 of 1 over x squared does not exist. It fails to exist due to unbounded behavior. Unbounded behavior. Now, we should also point out you could, DNE unbounded is, a good answer, but there's a difference between is it heading up to positive infinity or is it heading down to negative infinity. In this case, since they're both heading up to positive infinity, we could write this limit as we approach 0 is infinity, which does not exist, unbounded behavior. All right, so 2 reasons why we would not have a limit that exists. We're approaching 2 different numbers from the left and the right, or we have unbounded behavior to positive or negative infinity. The last one is right here. Example 8, they sort of spoil the surprise. Another reason a limit will not exist is oscillating behavior. So to explore this one, they give us this function, discuss the existence of this limit. We're approaching 0 of sine 1 divided by x. Kind of a weird function, but you'll see why they picked that specific one in a minute. And then they also pick some very odd x values to put in. Here's our 0. As we approach from below, we got negative 2 over pi, and then negative 2 over 3 pi, negative 2 over 5 pi. Again, those seem odd x values, but notice our denominators are growing. 1 pi, 3 pi, 5 pi. The closer we get, the bigger the denominator gets. Think about a fraction. The bigger the denominator means the fraction is smaller. So here's 1/10, 1/100th, 1,000th. As that denominator grows bigger, this is getting a smaller and smaller value, and we are approaching 0. So again, these seem odd, but watch what happens when we start plugging some values in. Here on the plus side, we get the same reflections of those. 2 over pi, 2 over 3 pi, 2 over 5 pi. As we get closer to 0, our fractions are shrinking in value. So let's see here. We've got the first one. We've got this 1 over x. I want to put in negative 2 over pi. So this x becomes a negative 2 over pi. And then how do we divide one fraction by another? We invert and multiply. So this denominator is going to come up and flip. So this is now going to look like the sine of negative pi over 2. Aha! That's something we can get from the unit circle. Here's our xy axis. Negative a half pi would be this far. So that would put us here. What is our sine value at this point? Well, our sine value is our y value, so that would be negative 1. If I put this negative 2 over 3 pi in for this x, just like the last one, that's going to come up and flip. So now it's negative 3 pi over 2. So the sine value of that, again, we're going negative, so here's negative a half pi, negative 1 pi, negative 1.5 pi, negative 3 halves. That y value, that sine value is positive 1. Negative 5 halves pi goes in. Same thing, that's going to come up and flip. So this is the sine of negative 5 halves pi, or negative 2.5 pi. So if I'm starting here, here's negative 2 pi, here's negative 2.5. So we're back down to negative 1. So here, as we're approaching in from the left side from below 0, our function's not settling down. It's not approaching one single number. It's bouncing around erratically. Negative 1 to positive 1 to negative 1. We could keep the pattern going, and it's just going to constantly be bouncing back and forth. We'll see something similar on the other side of 0. Here the only difference is now the negative is gone. So when I put in this 2 over pi, it just comes right up and flips, and now it's the sine of pi over 2. That's positive 1. If I put in the 2 over 3 pi, that will come up and flip and now be the sine of 3 pi over 2. Well, that's just right here. Back down to this bottom part of the unit circle, negative 1. 2 over 5 pi is back to positive 1. So again, the function is not approaching a single number. It's not settling down on a number. It's actually bouncing very erratically, or what they call oscillating behavior. And here's the graph of that. And the thing is, the closer we get to the y-axis, the faster the oscillation becomes. The closer we get, the faster it's going. It's going to bounce back and forth without ever touching the y-axis. So think about this, I could put negative 1 way over here. I could make this negative 0.001. I could start this from here and tell you there are infinitely many oscillations between negative 0.001 and the y-axis. There's always going to be infinitely many. The closer you get, the more the function freaks out, the faster it oscillates. And that is, again, another reason why a limit will fail to exist: oscillating behavior. So here when they ask us what is the limit as x approaches 0 of sine 1 over x, that limit does not exist due to oscillating behavior. Now, I'm a math teacher. I'm not an English teacher. If you misspell oscillating, as long as I can sort of tell what you were trying to spell, you will get full credit. OSC ends in ing, oscillating behavior. Spelling does not matter in math class. So here, let's sort of a little recap. Conditions under which limits fail to exist. The limit of f of x as x approaches some number c does not exist when any of the conditions listed below are true. 1, f of x, our function, approaches a different number from the right side of c, and then it approaches from the left side of c. Different left and right hand behavior. Number 2, our function f of x increases or decreases without bound as x approaches c. Unbounded behavior. Remember to differentiate between a positive infinity and a negative infinity unbounded behavior. Number 3, f of x, our function, oscillates between two fixed values of x, or two fixed values as x approaches c. Usually you're going to see a sine or a cosine function involved with oscillation. Here's a couple for you to try. Discuss the existence of this limit. Limit x approaches 0, negative 1 over x squared. You might want to check it from the left side and the right side, see what you figure out. And then here discuss the existence of this limit. So pause the video, try the problems, and then fire it back up and see if you get them right. Okay, this first one here is very similar to the one we did in the example. The only difference here is this minus sign. So let's think about what's that's going to do to this. When we did not have the minus sign in that earlier example, we had sort of this volcano-looking graph. Because we did not have the minus sign there, our function entirely existed on the positive portion of the y-axis here. So if I make this into a negative, that's just going to pull my graph down into the lower two quadrants. You could verify this by putting in some sample numbers, or take the same numbers we used in the example and just adding a negative in front of them. So here we can write the limit as x approaches 0. I'm just going to write it as f of x. That limit is a dne negative infinity. dne, it does not exist due to the unbounded behavior. I guess I could put that in there too. Unbounded behavior, and in this case we are headed to negative infinity. We're approaching 1 cos of 1 over x minus 1. Again, we always try direct substitution first. If I try to plug in that as a 1, I get 1 minus 1, or I'm trying to take the cos of 1 over 0. And that's not going to happen. We cannot divide by 0. It's a cosine function, and we're approaching that number, that 1 from both sides. That's going to tell us it's going to be oscillating behavior. We could, we'd have to carefully select out our very specific x values like we did here, to get that to work. But again, just like in the example, we see as we get closer to that number that causes division by 0, here we were approaching 0 because that's what would cause our division by 0 in example 8. But in this case, we're approaching 1, which is going to cause our division by 0 here. 1 minus 1 would be 0. It's cos, so that's going to be an oscillating. This, we can just say it does not exist. Our limit fails to exist, and that would be due to the oscillating behavior. The assignment for this section, we have 4 problems here. Again, these are always in WebAssign. If you're having trouble with the WebAssign program or your laptop, page 827 in the book, these 4 here will do. I hoped the video helped.